Okay, rates of change, differentiation, integration. Let's get going on this. The first problem here is part A, working out this height. We've got a circular cone, water dripping out of it at a certain rate, 2 centimetres cubed per second. What's the height after time t? Well, we want to know h, so let's write down things with h in that we already know. Volume of a cone is 1/3 pi r squared h. That's true, it's got h in, but it's also got v and it's got r squared in. If I can get rid of the v and the r squared, get those in terms of t, that would do. Other things I know about this, well, I've got an angle here and I've got a height, so what I'm going to do is I'm going to have a little look at the trigonometry of this. There we have a right angle triangle. There's the radius, and that would be 30 degrees. So tangent of 30 degrees, opposite over adjacent. And so I've got the radius equals h, tangent of 30, and the tangent of 30 is one of those angles that we need to know, and it is 1/√3, so r equals h/√3 and r squared, which I'm going to use in here, 1/3 of h squared. Let me put that in, see where that gets me. So I've got a volume, it's 1/3 pi r squared over 3 and times by h as well. So 1/9 pi h cubed. That's not so bad. If I turn this round, I can say what h cubed is. So h cubed, 9 times v over pi, and h would be the cube root of that, and I've got a cube root here, but what I've still got here is a v, so I've got to get rid of the v. Going back to my question here, I've got water is dripping out of the container at a constant rate of 2 centimetres cubed per second, and this thing starts off full. Now water drips out at a rate of, so dv dt, dripping out, so it's a negative, it's going down, -2 is the rate, centimetres cubed per second. If I integrate this, easy integration, so if dv dt is -2, then v must be -2t. Differentiate that and we get that. But of course, if we integrate, we get constants that we didn't know that were there, that differentiate and disappear. And the constant, if we put t equals 0 in here, volume is left as c. Because this starts full, we need the volume at full, and that is, volume is 1/9 pi h cubed, and full, h is 10, so that's 1,000 h cubed. H cubed is 1,000, should I say, and so when t is 0, volume has got to equal this, so volume equals -2t plus this thing, 1,000 pi over 9. And in fact, if we think about it, this makes a lot of sense. We could have written this down actually without doing this little calculation here. 1,000 pi over 9, full volume, -2 centimetres cubed per second. And so that's that's our volume. All we've got to do now, I think, is we've got to put this volume into this thing here. So we have got, oh crikey, what's gone on there? wasn't quite what I wanted to do. We want to put the volume in this thing there, and so we've got h cubed equals 9 over pi times pi v and so h cubed equals, multiply through by 9 over pi, cancels, and we get 1000 minus 2 9s are 18 t over pi, and if we cube root this, we have got our h equals. So this is done. Shrink that down. Second part of this question. The rate of change of the surface area. Now, if we want rates of change, then the things to do is to look at the rates we've already got. There was one that we had up here that I'm going to use, or at least I'm going to write down. So I know already dv dt equals minus 2. Other things that I know, well, I know volume is going to be, I've got it up here, I know volume is pi h cubed over 9, and so if I differentiate dv dh, 3 pi h squared over 9, and so dv dh is pi h cubed over 3. Sorry, pi h squared over 3. Okay, so I have got this one, and I've got this one. And other things I know, well, I also know that, well, I know the area, surface area there, the area of that surface is pi r squared. Now, pi r squared, I'm not using r, I'm using h's. Pi r squared is pi h squared over 3. It's the area of the surface, and I can differentiate that one as well. dA dh, 2 pi h over 3. And as is often the case with these, what we do is we take the differentials we know, those are those, and we see if we can put them together to give us a differential that we want. And the one we want is dA dt. Sling all these together. We've got a dv dt. That gives me the dt. I don't want the dv. If I don't want the dv, I need to cancel it by multiplying, and I'm going to use this one for that. I'm going to have to turn it over, flip it over to do so. And the only one I've got left is this one, which conveniently gives me the dh and will cancel out, sorry, gives me the dA and will cancel out the dh. So if we look at that thing, we'll notice that the dv's cancel, the dh's cancel, and dA dt is left. That's what I want, which means that I should be able to use those three and get what I need. So away we go. dv dt minus 2. dh dv, turn this one over. 3 over pi h squared. And dA dh, 2 pi h over 3. And if we put all that together, a bit of cancelling can be done. Pi, 3 h, one of the squareds, and minus 4 over h is what's left. So dA dt equals minus 4 over h, and don't forget h I've got over here, which is the cube root 1000 minus 18t over pi. And in fact, rather than let me save myself a little bit of space here, let's get rid of the t. And I know t is 15, so that's 18t, 18 times 15 over pi. I put this in my calculator, I should get my answer. So, calculator to hand. Cube root. Okay, that is our answer. Minus 0.412. Minus 0.412. And that'll be centimetres squared per second. Complicated question, but first part, if we want h, write down all the things we can find with h and then combine. Second part, rates of change. Find all the rates of change we know and put them together to get the one we want. And that one's done. This is also one of those questions that if we couldn't do the first bit, then we could still have a go at the second bit and we could have used that formula because it was given to help us get the last bit, even though we might have missed those first few marks. And there we go, that question finished.